Hello everyone, welcome you all at Lokesh Sir Unlimited Study Zone. So we're starting our lecture number 4th for chapter magnetic material and magnetism. So now we are in the topic on the topic properties of magnetic material. And yesterday we have seen first formula that is of magnetic induction and it is also called magnetic flux density. Clear? Magnetic flux density. So as a quick revision, right? B is equals to number of flux per unit area. Okay. The number of magnetic lines of forces inside a magnetic substance crossing per unit area normal to their direction is called magnetic induction or magnetic flux densities. Then we have studied about intensity of magnetization. So intensity of magnetization, this is equals to I is equals to magnetic moment induced per unit volume. Clear? Then magnetic intensity or magnetic field strength. Now you may confuse. There is also magnetic induction is termed as B, and here is magnetic intensity. So this is very confusing term. Magnetic intensity and magnetic field strength. It is called magnetic field strength. Okay. So I suggest you don't use the term magnetic field strength. It will confuse you. Only use magnetic intensity. So magnetic intensity is denoted by H. Okay. So the capability of magnetizing field to magnetize the substance is called magnetic intensity. Okay. The capability of magnetizing field to magnetize the substance, like you have applied some magnetic field here. This is a magnetic field that you have applied as north and south, right? So on applying north and south, you apply there a magnetic field that is called B. Okay. Now, if you insert a magnetic material inside the magnetic field B, then there is a magnetization of this magnetic material. All right. Magnetization will take place. Understand? Magnetization of this material takes place. Then there is some certain ability of this applied magnetic flux density. This is the magnetic flux density, right? Now, it having some ability to magnetize this material. Yes. So it having some capability. So what is the capability of magnetizing field? It having some capability that is going to magnetize the material. So the capability of magnetizing field. This magnetizing field is what? That is B. To magnetize the substance is called magnetic intensity. It is denoted by H, right? Clear? Okay, so H for all the cases, for general cases, H equals to B by mu naught. Okay, H equals to B upon mu naught. So if uh, there is only air, then for air only in vacuum, H equals to B upon mu naught. Write this formula, very important. H equals to B upon mu naught minus I. I is the intensity of magnetization, right? Clear? So write the formula H equals to B by mu naught. The SI unit of H is same as intensity of magnetization I, that is equals to ampere per meter. Ampere per meter. As by the dimensional formula, you can subtract the same quantity having the same dimension. You can subtract only the quantities having the same dimension. If I talking about I, see here the dimension of I. M is the magnetic dipole moment having dimension ampere meter square, and V having the dimension meter cube. Meter square cancel, and will give the concept, the formula for dimension ampere per meter. So write down the dimension of H, magnetizing intensity, is ampere per meter. Clear? Yes. So formula for vacuum. So if there is a vacuum, see here, beta. This is North Pole and this is South Pole, right, beta? And the medium present here is a vacuum. In vacuum, there is no gases are present, so no molecules are there. Okay, no molecules, no such any type of molecules are there. So if no molecules are there, this means no atoms are there. So there is no way to generation of any type of dipole moment, because a dipole moment generate when there are molecular magnets are present over there. If there are no molecular magnet, there is no way to generate any type of molecular, you can say here M, capital M. Okay, so if vacuum is there, nothing will generate in the form of intensity of magnetization, because intensity of magnetization I is equals to M by V. So as I m equal to 0, so I becomes 0. So the formula H equals to what you have seen, B upon mu naught minus I. So for vacuum, I becomes 0. So H equals to B by mu naught. Clear, beta? So write this H equals to B by mu naught. So in vacuum, I equals to 0. Intensity of magnetization is equal to 0 because no atom presented as medium. The magnetic field intensity of a solenoid, magnetic field intensity, it is called magnetic intensity. Okay. So magnetic field intensity or magnetic intensity, not it is field intensity. So H equals to Ni. Right. This is another formula. When there is a source as current, then this formula is applicable. H equals to Ni. Okay. Source of current. Yes. You see here, the source of magnetism are the external poles. Okay. North and south. Right. But in the case of solenoid, when you have a solenoid, so you must know when there is a solenoid. Yes. So to induce the poles in a solenoid, there is a source of current I. I current is flowing from the different terms. So if n number of terms, then magnetizing force or magnetizing field H equals to N into I. Right? Okay. Okay. So right, the magnetic field intensity of a solenoid H equals to Ni, and it is independent of the material of the core of a solenoid. Yes, but when there is a source of current. Yes, source of current. Hmm. Next, when magnetic material is kept inside a solenoid, you see here there is a solenoid. To first consider the air core solenoid. Yes, this is a air core solenoid. Clear, beta? So in air core solenoid, magnetization, due to this current, there is a production of field surrounding this solenoid all the way north to south. So this field is induced in air. So there is a field B naught. Clear? So when magnetic material, but when you insert a magnetic material, look here. Yes. When you insert a iron rod or any rod, copper rod inside this coil, then this current will magnetize also this rod. Okay, yes or no? So there is also induction of one more field inside the material that is equals to Bm. So the total field is given by B equals to B naught air wala part plus B medium. Done. So total B equals to B naught plus Bm. So B naught is equals to magnetic field or magnetic induction due to magnetizing field, and Bm equals to magnetic field or magnetic induction due to magnetization of material. Okay. Yes. That is why the total field will increase when you insert any material inside a coil, right? Because initially it was B equals to B naught as no material was there. But when you insert a material there, an external amount of magnetic field induces, that is Bm, right? Yes. Clear? Now, next topic is magnetic permeability. So, word permeability reflect itself its meaning. Look here, if I write permeability. If you divide this term, then it is looking like permission ability, permit ability. Okay, so some sort of feeling is there like permit ability. Yes or no? It is my own concept. It is not given in any book. So, but this is helpful. Permit ability. No. See, there is a material. I am giving you two type of material. So permeability is the property of a material. Okay. So what type of property it is? If there is a material, one material wants that maximum number of lines are crossed over it through it. Okay, maximum number of lines. This permit to pass maximum number of magnetic lines of forces through it or magnetic flux through it. Okay. And the another one material, this material does not want to permit the lines of forces. This material avoids to pass the line of forces. Clear? So permeability is high for this material. So this mu1 and permeability is mu2. So mu1 is greater than mu2. Understood? So this material, the top one material, our material, magnetic material, is readily accepted the magnetization of itself. Okay. And the another material is not ready for magnetization in the given direction. Okay. In the given direction. Clear? Given direction means in the source direction, external magnetic field direction. So magnetic permeability, it is defined as the no, this is oh, you can say this is bad definition, not giving you at such feeling. So magnetic permeability means it is the ease, it's supposed to be ease of magnetization provided by the magnetic material. Okay? Magnetic material. Easiness. This is called ease. Ease of magnetization. Right? Ease of magnetization. Now, by formula, we have seen B equals to mu into H. We just have seen for air or vacuum, H equals to B by mu. Yes or no? Hmm. So, H equals to B by mu. So, by the formula, mu equals to, if you take mu, here, then mu becomes B upon H, right? So B is what? It is magnetic induction, right? V was magnetic induction divided by magnetic intensity. Intensity. Clear? Yes. So it is the ratio. It is defined as the ratio of the magnetic induction inside the magnetized substance to the magnetic intensity H of the magnetizing field. Clear? So mu is given by B by H. Yes, see here. B equals to, sorry, mu equal to B by H. Note, measure of conduction of magnetic lines of forces through a substance. Yes, so this is qualitative definition. It is the measure of conduction. And conduction means what is amount of easiness it will provide to the magnetic lines of forces for passing through the substance is called what? Permeability. Clear? So, permittivity is epsilon. That is in the chapter of electricity. Same concept, same thing is there, but there is change. There are electric lines of forces, but here it is magnetic lines of forces. The whole thing happens for magnetic lines of forces. Okay. So, units, this is equals to Weber per ampere meter. Okay, right. So, unit equals to a unit of mu equals to Weber per ampere meter. Sorry, the definition, this one. First, this one definition. Ease of magnetization provided by the magnetic material. Okay. Yes. Ease of magnetization. Yes, write the formula. B equals to mu h. So H equals to B by mu. Mu equals to B by H. Mu. Mu. Okay. The same symbol that is for using for refractive index. So this is called mu and denoted as mu. Greek symbol. Okay. Now unit is Weber per ampere meter. Unit is Weber per ampere meter. How? B, the unit of B is equals to uh, Weber, unit of B. You know, B is equals to phi upon A. Yeah, Tesla. It can be written as Tesla also. So if you write SI unit, so Tesla and H is ampere per meter, right? We just have derived the unit of H. Here it is ampere per meter. Okay, yes, ampere per meter. So it will go upside. So this will become Tesla meter per ampere. Clear? So it will become Tesla meter per ampere or TMA inverse. Also Weber per ampere meter. Weber per ampere meter. Okay. Hmm. So Weber per ampere meter, you also see me equals to B by H. So B is equals to phi upon A means Weber per meter square divided by H. H equals to ampere per meter, right? So Weber per meter square into meter upon ampere. Meter cancel. Answer Weber per ampere meter. Clear? In this way, you can obtain the unit of mu, Weber per ampere meter. So both the units are clear. Okay. Now relative magnetic permeability. Yes. See here. Actually, when there is a material, it having some permeability mu. Okay. So mu equals to the permeability of the any magnetic material. Suppose this is mu medium. commonly written as mu. So mu medium is exactly some multiple of permeability of air, because this is the fundamental basic reference permeability of air. So it will be some multiplication of fundamental permeability. Understood? Like if I talk about relative density. So density of any material is equals to relative density multiply density of water. Okay. So relative density, the formula is equals to density of material divided by density of water. Clear? So here mu r relative permeability is equals to permeability of the medium divided by permeability of the air. Right? When you compare the permeability of any medium with respect to permeability of air, the factor came out is called relative permeability. Okay. The meaning of relative permeability is with respect to air, in comparison of air, your material will give how much ease for the magnetic field in comparison to air. So it is the ratio of the magnetic permeability mu of the substance or medium to the permeability of the free space. So very simple, relative permeability mu r is equals to mu of material by mu naught. Right, beta? Yes. If your medium is air, so this is medium is air. So for air, mu r equals to mu medium, your medium is air and you are relating with air, so answer equals to 1. So for vacuum or air, relative permeability equals to 1. Clear, beta? Yes. So note it down, mu r equals to mu by mu naught. Okay. Now you can also define mu r as b by b naught. Okay, so it is also defined as the ratio of the magnetic field b in any substance. This is B for any substance. You can also consider it B in any medium and divide by B naught. Okay. So B for any medium, when medium is present, their permeability of the medium is mu and magnetizing force B equal to mu H. Here we have studied, yes, this one. B equals to mu H. Okay. So B equals to mu H and B naught equals to mu naught into H. H and H will cancel out and it will give me by mu naught. Clear? So mu by mu naught equals to mu r. So mu r can be also defined as the ratio of the magnetic field B in the substance when placed in magnetic field B naught. Okay? Clear? So mu r also defined as the ratio of magnetic field B when you apply the magnetic field any given substance. So it will considered as B with comparison to magnetic field in air or vacuum B naught. Clear? Yes. Very important lines. We are going to study three type of material. So journey actually starts from here. As there are three type of materials, for paramagnetic material, relative permeability is slightly greater than 1. Yes. Relative permeability is slightly greater than 1. Means if you have paramagnetic material, it will support the magnetization in feebly, you can say minute support is there. Okay, because permeability is greater than 1, slightly greater than 1. Clear? Relative permeability is greater than 1. Yes. Understood? Second, for ferromagnetic material, this is for paramagnetic. For ferromagnetic material, mu r is very, very, very greater than 1. So it support heavily the magnetization. Okay. So this is called ferromagnetic. And for diamagnetic, mu r is less than 1. Yes. So there will be a feeble, you can say, restriction or repulsion towards the propagation of magnetic field inside this material. Okay. So this is diamagnetism. Clear? So in the diagrammatic way, if there is a magnetic field, some type of magnetic field, and there are different type of sample. One is ferromagnetic, second one is diamagnetic, and upper one is paramagnetic. Sorry, first it is dia. Then see, these are the lines of forces. So dia will respond like this. Okay. Now para will respond like this, and ferro will respond like this. Ferro will e- para. There is, see here, most of the in diamagnetic material, the material does not want to permit the lines of forces through it. Okay, only few lines are permissible to pass. Okay, and most of the lines are permitted not to pass. They are just fringe away. Okay, here few lines are passed. Okay, but some lines are there which may not be passed through the material. Some of them. Okay, here only one is passed. You can see only one. Here three which are at the center line. Okay, are passed. But here this material correct all the lines, even the line coming from here. Okay, this material say, hello, sir, please penetrate me. Okay, so this material offer to pass through itself, right? So here relative permeability is very high. It is very greater than 1. Here it is just greater than 1, and here it is less than 1. Clear, beta? Yes. So this is about type of material: ferromagnetic, diamagnetic, paramagnetic. Next, it is topic magnetic susceptibility. Yes, very, very important. This relative magnetic permeability was important. Then now this is also very much important. Magnetic susceptibility. Magnetic susceptibility of a material indicate how easily material can be magnetized. Okay, how easily material can be magnetized. Clear? See, on applying magnetizing intensity H, yes, see here, magnetic intensity H, if on applying I, sorry, H magnetizing intensity, there is I. I is what? Yesterday we have learned I, intensity of magnetization. Clear? So both the terms are very much confusing. H is magnetizing intensity and I is intensity of magnetization. So on applying H magnetic intensity, there is I magnetization developed. Then on unit magnetizing intensity, development of magnetization, intensity of magnetization is I by H. Okay. So this is called magnetic susceptibility. This is called chi m. Yes. Yes. The magnetic susceptibility of a material indicates how easily a material can be magnetized. It is defined as the ratio of intensity of magnetization I in a substance to magnetic intensity H applied to the substance. Okay, beta? Because magnetic intensity H is a thing to apply. And when you apply H, in how much amount magnetic volume, magnetic dipole created. So this will give a term xm. This is called chi m, right? So chi m is equals to intensity of magnetization per unit magnetic intensity, right? Intensity of magnetization per unit magnet magnetic intensity. Okay. Hmm. So it is a scalar quantity with no units as I and H both having the same unit. So they will cancel each other. Ampere per meter will cancel out, and they having the same unit scalar quantity. It will be a constant, right? Okay. Now next between relation between mu r and chi m. This is very important relation and going to lead the Curie temperature concept. Now, relation between mu r and chi m. Consider current carrying toroid having core material relative permeability mu r. The total magnetic flux density of the material is given by, as I said you here, yes, look here. The total magnetic induction is given by B naught plus Bm. Yes or no? So once again, start from there. B equals to B naught plus Bm, right? Now, B equals to B naught. In the place of B naught, you write mu naught H. Clear? And B magnetization equals to mu naught into I. So B naught is the magnetic flux density due to current in the coil. Magnetic flux density due to current in the coil B equals to B naught. And B magnetic is the magnetic flux density due to the magnetization of material. Because when there is a coil, so first, without magnetic material is there, there is uh, magnetic flux density, a magnetic field will set up here. So the magnetic flux density is called B naught. And when a magnetic material is placed inside it, so there is also magnetization of magnetic field. So develops a field that is equals to Bm. So B naught plus Bm equals to mu naught into I. Now put here the value. You can take B mu naught as common. So it is equals to H plus I. Right, beta? B equals to mu naught H. Fine, it is. Now I. We just read chi m for material equal to intensity of magnetization I divided by H. Okay? Yes or no? I divided by H. So in the place of I, you can write chi m into H. Here I equals to chi m multiplied by H. Clear, beta? So you can place chi m multiplied by H. Chi m is the magnetic susceptibility. Clear? Okay. So B equals to, you can take out common, B equals to mu naught into H, and this is equals to 1 plus chi m, right? And for the whole material, B equals to what? B equals to mu naught into mu r into H. Yes, this B equals to mu naught mu r into H. Why? See here, as B equals to mu into H, B equals to mu medium into H. Okay, B equals to mu medium into H. Got the point? Now, you know, relative permeability is equals to permeability of the medium divided by permeability of the air. So, mu medium equals to mu relative into mu air. Clear? So, mu relative into mu air. So, if you put here B value, the value of B equals to mu R into, see here, B equals to, in the place of mu material, I can place mu R into mu naught into h. So beta, place here the value mu naught mu r h, and here it is mu naught h 1 plus chi m. Now mu naught cancel, h and h is also cancelled. So the value of mu r equals to 1 plus chi m. Understood? Yes. So this is the value. This is the relation between relative permeability and magnetic susceptibility. Okay. Note it down. Now, next topic is cause of dimagnetization. So before going cause of dimagnetization, try to understand orbital theory of magnetization. This is the part of chemistry. Okay. You must have learned about in D block element. There are few elements are paramagnetic and diamagnetics. Depend on the spinning of the valence electron. Yes or no? See here. So paired and unpaired type of electrons. Like there is an electron, and if electron is revolving like this in opposite direction, in this direction, this is the direction of electron. Okay. So current will produce in the opposite direction of its spinning moment, opposite to the direction of moment. So yes, take out your right hand and again curl your fingers in the direction of current. So this is the direction of current. You see a magnetism is produced, magnetic moment is produced in this direction. Yes or no? It is also possible that magnetism is produced in the downward direction. So there are two cases maybe there, right? So cause of diamagnetism. Cause of diamagnetism. First, try to understand what is diamagnetism. So when there is a material, especially diamagnetic material, then what happens? So suppose this is a sample of diamagnetic material. Okay, all the diamagnetic material have paired electrons. Remember, there are paired electrons, paired number of electrons. Okay, in their valence orbit, like magnesium, beta, like magnesium. So magnesium have total 12 number of electrons. Clear, beta? So 12 number of electrons. So if you fill the electrons, then there will be a configuration at 2, then 8, 1, 2, 3, 4, 5, 6, 7, 8. Okay? 2, 8, and 2. Clear? So there are all are paired electrons. Even number of electrons means paired number of electrons, right? So in diamagnetic material have paired number of electrons, in their valence orbital, which produces equal and opposite magnetic moment. Hence they cancel out each other. Thus effect and resultant magnetic moment equal to 0. Like see, here is some sample. In the outermost orbit, there are how many electrons? 1, 2, 3, 4, 5, 6, 7. Okay. 7 orbitals are there, each having two clockwise and anti-clockwise spin of the two electrons, as you have seen in orbital theory. One is going upward and second one is going downward. Yes or no? You must feel such like a structure in Hundsul class 11th. Yes or no? Okay, so two electrons are there, two paired electrons are there. So beta, as they spinning in the opposite direction, so they will produce equal and opposite magnetic moment. So the net magnetic moment equal to 0. Clear? Clear. So when there is no field applies, no any magnetic field applies, so the magnetic moment equal to 0. Clear, beta? When external magnetic field is applied, yes. When external magnetic field is applied, then what happens? See here, two type of spinning are there. Naturally, without applying the field, here two type of spins are there. One magnetic moment here, and another one's magnetic moment is going in this direction. Both are equal and opposite. But as you applied the field, as you applied the field, clear? As external magnetic field is applied, electron producing magnetic moment along the external magnetic field slows down. Electron producing magnetic moment along the external magnetic field. See here, the electron, the green one electron. Okay, see here, this the green one electron that producing the magnetic moment, it will slow down. Okay, and second, the electron producing magnetic moment opposite to the external magnetic field, it will is speed up, right? So what will happen? Beta, देखिए, the first electron will be slow down. So here the green one will be slows down and this will be speed up. Okay. So resultant magnetic moment. Now see, this vector becomes larger and this vector become smaller. What happens if there are in orbital two spins are there? So in the opposite direction of propagating field or is magnetic field, applied magnetic field, this opposite vector will become larger and this become a smaller. Why? Because the applied magnetic field slows down the magnetic moment in direction to it. Okay. So see here. So resultant magnetic moment is not equal to zero. Previously, when there is no field applied, they will cancel each other, both the fields, both the magnetic moment, and the resultant magnetic moment was zero. But here the magnetic moment not equal to zero. Clear? Clear? So the resultant magnetic moment not equal to zero, and the resultant magnetic moment opposes the external magnetic field. Why? See here, if you count the resultant of these two vector, so this is larger and this is smaller. So the resultant will be in this direction. Yes or no? Okay. So the resultant will be broken out in the leftward. But your applied field in right direction. Okay. Understood? So this is why paramagnetic materials are magnetized feebly in opposite direction of the magnetic field. Okay, write it. Diamagnetic materials. Diamagnetic materials magnetized in opposite direction, feebly magnetized. Okay, feebly magnetized, not very much strongly. They don't have such magnetic moment of very large magnitude. So diamagnetic materials feebly magnetize in opposite direction of applied magnetic field. Understood? Diamagnetic materials are feebly magnetized in opposite direction of the applied magnetic field. Yes. So such a like event takes place and there is a net magnetism will produce opposite to the direction of applied magnetic field. Yes. Next, cause of paramagnetism. Okay. Cause of paramagnetism. Atom in paramagnetism are unpaired electron. There in diamagnetism, there are paired electron. And in paramagnetism, there are unpaired of electron in the outer subshell are in the motion, hence produce magnetic field in random direction. Okay. So when there is no field applied, so the magnetism produced, the magnetic moment produced in random direction. And in external magnetic field, the magnetic field align to the direction of external magnetic field. See here, there is only one electron. When you applied any magnetic field, so the magnetic moment of the this electron align with the applied magnetic field. So they will produce a net magnetic moment in the direction of magnetic field. Okay. So what is change here? In paramagnetic substances, For diamagnetic, there is a feeble magnetism in opposite to the direction of applied magnetic field. In paramagnetic substances, a feeble, because only one electron is there, so feeble magnetism ism in direction of applied magnetic field. Nitin, understood? Direction of applied magnetic field. Note it, important. Yeah, it also have feeble magnetism. Paramagnetic substances, paramagnetic substances, having feeble magnetism in direction of applied magnetic field. They having feeble magnetic dipole moment in direction of applied magnetism. Right? Yeah, now look, cause of ferromagnetism. So, cause of ferromagnetism can be explained by domain theory. So, here, in the absence of applied magnetic field, there is no B is equals to 0 in first sample, B equal to 0. Look here, these are called molecular magnets, and the collection of molecular magnets are called domain. These are called domain. Okay. So, atom in ferromagnetic material with unpaired electron in outer subshell, here they are just distributed like this. But when you apply a magnetic field, they are get aligned in same direction and will generate a higher magnetic dipole moment. They are aligned with another in the same direction. Okay. And they will generate a higher magnetic moment, capital M, in the direction of applied magnetic field. Okay. Yes, these domains easily align themselves in one direction in the presence of external magnetic field, and they will generate a great magnetic moment in the direction of magnetic field, applied magnetic field. So in ferromagnetic field, they ferromagnetic material materials produce a strong magnetism, okay, in the direction of applied magnetic field. Yes. So they feel as strong. Produce is not correct word because there is not such a production. There is actually type of realization. So there is a realization of a strong magnetism. Okay, in the same direction of applied magnetic field. Yes. So this is the reason between the three type of material for their different type of behavior: diamagnetic material, paramagnetic material, and ferromagnetic material. Understood? Now, one important, very important, and most obvious question of uh, this chapter, there is a comparison between diamagnetic, paramagnetic, and ferromagnetic material. Based on all the theory that we have read out here, there is a comparison. First, diamagnetic first. These materials are weakly repelled by the magnet. Yes, as you've seen, there is a feebly magnetization takes place in the direction opposite to the magnetic field. Yes or no? So this will reflect what? This will reflect these materials are weakly repelled by the magnet. So these there is feeble magnetization against to the applied magnetic field. So there is weakly repelled, right? They are weakly attracted by the magnets. These material are weakly attracted by the magnet, and here it is. These material are strongly attracted by the magnet. Clear? In external magnetic field, they acquire weak magnetization opposite direction of H. I have shown you in the diagram. M is in opposite direction to the applied magnetizing intensity, right? You applied H here in this direction. So in responding to H, there is a feeble magnetic moment rising up in the opposite direction of applied H, right? Here as a feeble magnetism develops, magnetic dipole develops acquired magnetization, feeble, weak magnetization in the direction of H. And here, strong magnetization, acquisition of strong magnetization in the direction of H. Understood? Yes. Very before we have talked about this, you see in this, here, this one slide, diamagnetic material. Yes or no? So in diamagnetic material, there are the lines of forces bends away from the diamagnetic material. This material not want to magnetize itself, okay, because it is oppositely magnetized. So lines of forces are crossing over the material. Clear? So in external magnetic field H, M line bends away from the diamagnetic material. Here, external magnetic field H, few magnetic lines little bend towards the paramagnetic substance. Okay, and which are far away from the magnet, they will say, who cares? Just passing out of the magnet. Okay, but here, this will provide a great permeability. Okay, welcoming all the lines of forces as mu r is very greater than 1. So in external magnetic field, most of the magnetic lines bend towards the ferromagnetic materials. Okay. Resultant magnetic moment here is zero in the absence of magnetic field, you see. Okay. Resultant magnetic moment here, it is not equal to zero, but very small, have permanent magnetic moment. Yes. And here resultant magnetic moment is not equal to zero, have permanent magnetic moment. Clear? Yes. So in diamagnetic material, we have learned that, yes, have paired electrons in the valence orbitals, so which produces equal and opposite magnetic moment. Yes. Okay. So in case of diamagnetic moment, the resultant magnetic moment is always zero. Clear, beta? Yes. So they are unpaired. So magnetic moment is there. And here also unpaired electrons. So magnetic moment is also there. Having permanent magnetic moment, both paramagnetic and ferromagnetic, right? If there is non-uniform field, diamagnetic material will move towards weaker section because it hit from the strong magnetization. So it will traveling from left to right. Okay, slowly, as it feels feeble magnetization opposite to the direction of magnetic field. So it will repel from the strong magnetization area, right? It will attract it towards para, P for para. Okay, so it will attract it towards the stronger section, but slowly. Okay, but non-uniform field ferromagnetic material move towards strongest section very quickly. You see here, it is moving quickly than the previous one. It is at the end of the region there where the magnetic field is very high. Yes or no? So it is moving towards the strongest region. Now, for example, bismuth, copper, alcohol, mercury, etc. Here, sodium, aluminium, okay, calcium, oxygen, copper chloride are the example. You must learn them. At least two example you must learn. And iron, nickel, and cobalt. Okay. Yes, in chemistry, this is FeCO Ni. Okay, lying on the same period in D block. Magnetization is almost independent of temperature. Yes, very important. Here, the magnetization is independent of temperature. No effect on the magnetization when you heat up the material. Magnetization is inversely proportional to the absolute temperature. Clear? Magnetization is inversely proportional to the absolute temperature. Magnetization depend on temperature. At high temperature, they become paramagnetic. Clear? One more thing here, magnetic susceptibility is inversely proportional to temperature. Clear? Write this one. Magnetic susceptibility is inversely proportional to temperature. And here, magnetization depend at temperature. At high temperature, they become paramagnetic. So at the temperature, they become paramagnetic is called Curie temperature. See here, if I make the diagram of magnetic susceptibility chi m, versus absolute temperature. So up to the Curie temperature, there is no particular variation of magnetic susceptibility. But after Curie temperature, there is an exponential decay in the magnetic susceptibility. Okay, and here the uh, your substance was previously Curie temperature, the material was ferromagnetic. Okay, up to this reason here it was ferromagnetic, but here it converts into the paramagnetic. Okay, paramagnetic. And in paramagnetic, what is the relationship? Xm, magnetic susceptibility, is inversely proportional to the temperature. So that's why it is relationship varying here, the value of chi m as inversely proportional to the temperature. But remember, after Curie temperature. Okay. So after the Curie temperature, the ferromagnetic material behave as a paramagnetic material. Yes. Magnetic susceptibility is negative. Yes, because it is creates its magnetization in opposite direction. Clear? Magnetic susceptibility is negative. Here the magnetic susceptibility is positive but is small. Here the magnetic susceptibility is positive and very large. Clear, beta? We have already talked about the permeability. Permeability of the material is lesser than mu naught. That's why mu r is less than 1. Okay? Because mu r equals to mu by mu naught. So when denominator is greater and material is lesser, so mu is less than mu naught. So mu r is less than 1. Here, applied material having the permeability greater than the air or vacuum. And here the applied permeability of the material is very, very, very much greater than the vacuum. Clear? So three things are there. Now, if diamagnetic material are freely suspended, they align itself in the perpendicular direction. You see here, this is the north south. Okay, and you align this material, so it this material wants to expose the minimum area towards the field, so it will align itself to the perpendicular. Okay, sorry, here it is diamagnetic, but here it should be paramagnetic. Make it correct, it is not diamagnetic, this is paramagnetic. Okay, paramagnetic material freely suspended external magnetic field, they align itself parallel to the magnetic field. Like if there is a paramagnetic material, and if you suspend this rod like this, then it will align itself in the direction of magnetic field. This rod to want to propagate maximum number of lines of forces through it. Okay, but in slow way. But if you align here in north south direction a rod of magnetic material, it will align itself very quickly. Fatak say, okay, very quickly it will align itself in the direction of field. Clear? Clear? Yeah, diamagnetic solution is there in a YouTube. When you place in this YouTube, there is a magnetic field. So this want to become far away from this magnetic field. So the level of one side will falls and the another side will be risen up. Clear? Yes, diamagnetic material want to minimum exposure of itself towards a field. And here, if there is north-south magnet, so there is a rise of liquid. Okay, this is a paramagnetic solution. So paramagnetic solution wants to align itself in the magnetic field direction. So there is a rise here in left side. Okay, and if you place a ferromagnetic solution, then there is a very quick response. Okay, in very quick manner, the liquid will rise up. Done. So this is complete our chapter. Theoretical part is completed of this properties of magnetism. We have completed each and every point of this chapter. Done.